Section: Introduction. In this section, we discuss the widespread use of spreadsheets in data management, such as Microsoft Excel and Google Sheets. Understanding how spreadsheets are organized is crucial for effective data analysis and user interaction. Large language models, LLMs, have shown promise in processing tables, but they face challenges with the complex layouts and features of spreadsheets. To tackle this, we introduce SPREADSHEETLLM, a framework that aims to enhance LLMs for better understanding and reasoning with spreadsheets. Initially, we propose a method to convert spreadsheets into sequences, including important cell addresses and formats. Large spreadsheets can overwhelm LLMs, leading to reduced accuracy. To address this, we introduce SHEETCOMPRESSOR, which includes three key components. 1. Structural anchors for efficient layout understanding, identifying key rows and columns that provide crucial layout information and removing unnecessary ones to simplify the spreadsheet structure. 2. Inverted index translation for token efficiency, using a dictionary to index cell texts and optimize token usage, especially for spreadsheets with many empty cells or repetitive values. 3. Data format aggregation for numerical cells, grouping adjacent numerical cells with similar formats to streamline data understanding without using excessive tokens. Our evaluation shows that SHEETCOMPRESSOR reduces token usage by 96% and improves spreadsheet table detection by 12.3% compared to previous methods. We also introduce Chain of Spreadsheet (CUS) for spreadsheet QA tasks, outperforming existing methods. Our contributions include proposing SPREADSHEETLLM to enhance LLMs for spreadsheet analysis, introducing SHEETCOMPRESSOR for efficient encoding, and demonstrating the effectiveness of CUS for intelligent user interaction. In related work, various methods have been explored for representing spreadsheets in different models, such as using LSTMs for sequential semantics and pre-trained LMs for understanding spreadsheets. While Markdown and HTML have been used for table representation, they are not ideal for complex spreadsheet structures. Section Summary. In this section, we introduce SPREADSHEETLLM, a novel framework that leverages large language models, LLMs, for understanding and analyzing spreadsheet data. To address challenges in processing large and complex spreadsheets, we propose SHEETCOMPRESSOR, an innovative encoding framework that significantly reduces token usage for LLMs. Through comprehensive evaluations, we demonstrate that SPREADSHEETLLM excels in spreadsheet table detection and reasoning tasks, outperforming previous state-of-the-art methods and showcasing its potential for intelligent user interaction. Section: Spreadsheet Understanding. In this section, we delve into the realm of spreadsheet understanding. We have observed that while most table language model, LLMs, are limited to single table scenarios, dealing with spreadsheets containing multiple tables often surpasses token limits. The diverse layouts and structures of multi-table spreadsheets further complicate the issue. The primary goal of spreadsheet table detection is to identify all tables within a sheet and determine their respective ranges. This task is crucial for understanding spreadsheets and is heavily utilized in commercial spreadsheet tools daily. However, there is still room for improvement in accuracy due to the intricate nature of spreadsheets. Spreadsheet understanding opens up a range of tasks such as table question answering analysis, table extraction, formula or code generation, and error detection. In this paper, we focus on spreadsheet question answering, QA, which is a highly sought-after analysis task. It builds upon table QA by incorporating the challenge of detecting and matching multiple tables within a single spreadsheet. Previous work has shown that the performance of LLMs deteriorates when dealing with long contexts. To address this, various techniques have been developed to compress long prompts and enhance model efficiency. However, These strategies mainly cater to natural language prompts and may not be suitable for tabular data, potentially leading to significant loss of structure and data information. While tools like DB Copilot facilitate text-to-SQL conversion for large databases through schema routing, the limitations of LLMs in understanding complex multi-table layouts hinder their ability to execute queries similar to SQL, making schema routing impractical for cutting-edge tabular works on spreadsheet data. To tackle these challenges, we introduce a novel spreadsheet encoding framework in a Markdown-like text format. This framework comprises 3 modules: structural anchor-based extraction, inverted index translation, and data format-aware aggregation. These modules work independently but can be combined to achieve efficient data compression and enhance performance in downstream tasks. In our exploration of spreadsheet encoding methods for LLMs, we found that traditional approaches lack standardization. After comparing various tabular data encoding methods like HTML, XML, and Markdown, we opted for a Markdown-like representation due to its balance of encoding length and performance in spreadsheet understanding tasks. We also considered incorporating cell format information into the encoding but discovered that it negatively impacted model performance due to token limit constraints and ILM's limitations in processing format details effectively. Large spreadsheets often contain rows or columns with homogeneous data that do not contribute significantly to understanding the layout and structure. To address this, we devised a heuristic-based method called structural anchor-based extraction. This method identifies heterogeneous rows and columns at table boundaries, known as structural anchors, and discards rows and columns that are distant from these anchors beyond a specified threshold. By extracting these structural anchors, we can compress the spreadsheet while retaining essential layout and structural information. This method filters out a significant portion of spreadsheet content while preserving the integrity of table boundaries. Section Summary. In this section, we introduce a novel framework for encoding spreadsheets in a Markdown-like text format to enhance efficiency and performance in downstream tasks. Our approach involves 3 modules: structural anchor-based extraction, inverted index translation, and data format-aware aggregation, which collectively enable effective data compression while maintaining crucial layout and structural information. By focusing on extracting heterogeneous rows and columns at table boundaries, we significantly compress spreadsheet content while preserving the integrity of data relationships, resulting in a highly efficient text representation that retains essential structural cues. Section: Inverted Index Translation. In this section, we will explain how we improved the encoding method for spreadsheets to make them more efficient. Spreadsheets often have many empty rows, columns, and cells scattered around. The traditional method of encoding these spreadsheets involves pairing cell addresses with their contents in a grid-based manner. However, this method leads to recording empty cells, which increases the number of tokens needed. Additionally, cells with the same values are encoded repeatedly, further increasing token usage. To tackle these inefficiencies, we introduced a 2-stage inverted index-based translation method. In the first stage, we converted the traditional grid-based encoding into a dictionary format. Here, cell values act as keys that index the cell addresses. In the second stage, cells with the same value were merged, empty cells were excluded, and cell addresses were noted as ranges. This approach helped reduce the number of tokens required by removing redundancies and simplifying the representation of repeated and empty cells. This translation process significantly improved the compression ratio of SHEETCOMPRESSOR from 4.41 to 14.91. Moving on to data format-aware aggregation, we observed that adjacent cells in spreadsheets often share the same data format. By focusing on the data type rather than the exact numerical values, we can compress identical data types through clustering, reducing the number of tokens needed. We introduced the use of number format strings, NFS, to describe the format of cell data. Additionally, we proposed a rule-based recognizer to map cell values to specific predefined data types like year, integer, float, percentage, and others. By aggregating cells based on NFS and data type, we further reduced the number of tokens and increased the compression ratio from 14.91 to 24.79. Furthermore, we discussed the chain of spreadsheet, which involves table identification and boundary detection. Here, the model identifies the relevant table based on the query and determines the precise boundaries of the content, optimizing processing efficiency. In response generation, the model processes the query and table section to generate an accurate response. Through these steps, SPREADSHEETLLM effectively handles complex spreadsheets by breaking down the process into manageable parts, enabling precise responses. In our experiments, we validated the effectiveness of our method in spreadsheet understanding, starting with spreadsheet table detection. We then explored its applicability to downstream applications like Spreadsheet QA, testing the model's ability to detect, comprehend, and respond to user queries. We used a benchmark dataset of real-world spreadsheets with annotated table boundaries and implemented a quality improvement pipeline to ensure accurate labeling. This resulted in a validated test set containing 188 spreadsheets, divided into categories based on token usage. We evaluated our method using the error of boundary O, EOB0, metric on 188 spreadsheets with 311 tables to assess its performance accurately. Section Summary. In this section, we introduce an inverted index-based translation method to efficiently compress spreadsheets by converting matrix-style encoding into a dictionary format, merging cells with the same value, and excluding empty cells while noting cell addresses as ranges. This method significantly reduces token consumption and increases SHEETCOMPRESSOR's compression ratio from 4.41 to 14.91. Additionally, we propose data format-aware aggregation, which leverages number format strings, NFS, and predefined data types to further compress spreadsheet data regions, increasing the compression ratio to 24.79. These techniques optimize spreadsheet understanding tasks and enhance processing efficiency by accurately identifying relevant data and generating context-aware responses. Section: Baseline and Evaluation Metrics. In this section, we evaluated the performance of SPREADSHEETLLM by comparing it to TableSense CNN, which is a known effective model for detecting spreadsheet tables. We used the F1 score as our main metric to assess different models, as it considers both precision and recall, giving us a complete view of model accuracy. For our experiments, we selected both closed-source models like GPT-4 and GPT-3.5 from OpenAI, known for their strong language understanding abilities, and open-source models like Llama 2, Llama 3, Phi 3, and Mistral V2. We created a new Spreadsheet QA dataset that focuses on multi-table scenarios, unlike existing datasets that only cover single-table situations. This new dataset includes 64 spreadsheets with 4 to 6 questions each, testing basic operations like search, comparison, and simple math. To compare SPREADSHEETLLM, we used Tapix and Binder as baselines, adapting them for multi-table contexts. We fine-tuned our model to identify relevant table regions for each question and then fed this information into the baseline models. If the input was too large for the baseline models, we truncated it. We assessed answer accuracy based on the correctness of cell addresses and calculations provided. Our experiments mainly used the GPT-4 model due to its advanced language understanding and reasoning capabilities. We fine-tuned the model on spreadsheet table detection and conducted QA experiments following a specific procedure. We also applied compression techniques to handle large tables effectively. We evaluated the effectiveness of our encoding process by calculating the compression ratio, which measures how much we reduced the size of the spreadsheet data. Our encoding method achieved an impressive 25 times compression ratio, significantly reducing the computational load for processing large datasets. The results in table show the compression ratios for different module combinations within SHEETCOMPRESSOR. Our main results showed that the fine-tuned GPT-4 model achieved a 76% F1 score across all datasets, while our encoding method without aggregation reached 79%. This marked a 27% improvement over the original model, a 13% increase over TableSense CNN, and set a new standard. Our method also improved performance on larger spreadsheets and enhanced in-context learning capabilities. Additionally, we achieved significant cost reduction in our test set. Section Summary. In this section, we evaluated the performance of SPREADSHEETLLM by comparing it with TableSense CNN as a baseline using the F1 score metric. We selected various models like GPT-4 and GPT-3.5 from OpenAI and Llama 2, Llama 3, Phi 3, and Mistral V2 for experiments, adapting Tapix and Binder for multi-table contexts. Our encoding method significantly improved F1 scores, especially on larger spreadsheets, showcasing enhanced performance and cost reduction benefits, with detailed results provided in the appendix. Section: Ablation Experiment Results. In this section, we present the results of our ablation experiments for different modules. We observed that removing the extraction module resulted in significantly lower F1 scores, emphasizing its crucial role in capturing and preserving key structural information. The extraction module also showed the most substantial token reduction, indicating its effectiveness. Interestingly, when we removed the aggregation module, the F1 score slightly increased. This could be because the NFS method, being more abstract than straightforward numerical representations, can pose a challenge for LLMs to interpret effectively. However, the NFS method offered a significantly high compression rate, making it promising for practical applications and cost control. Moving on to the spreadsheet QA tasks, we analyzed the performance of various models. Our findings revealed the following. 1. The CUS method we developed significantly improved model accuracy by 22% compared to the baseline GPT-4 model. This method focuses only on relevant regions in large spreadsheets, addressing token limits and enhancing efficiency in handling QA tasks. 2. The fine-tuned model, trained on spreadsheet table detection, demonstrated strong generalization capabilities across different QA tasks, leading to a 6% accuracy improvement. It outperformed other models by a significant margin, showcasing the benefits of fine-tuning in understanding specific data nuances and improving overall comprehension abilities. 3. Our designed split method had a positive impact on QA task performance, increasing accuracy by 3% and 5% on ICL and fine-tuning, respectively. This enhancement allows LLMs to process tables that were previously challenging due to token limitations, ultimately boosting the performance of SPREADSHEETLLM.